Here's the story of Mr. Wade's evolution. I taught mathematics at this institution, but then came March. They postponed school. COVID-19 was playing us like a fool. I snuck back in and taught some AP, but they locked up the building and cut the AC. I got frustrated and wrote some sick rhymes. I filmed a rap video just to pass time. I started teaching lessons from my house in Brentwood. Oh wait, you're not supposed to see my real house. I started teaching lessons from my house far away, but I missed writing on a board every day. I talked to my friend Steve Smith, computer hacker. We had to find a whiteboard and he's no slacker. We looked around the city, we finally scored, and now I'm back teaching from a dry erase board. Now we're off Schoology, every single grade, and that's the story of the evolution of Wade.
All right, AB students, welcome to Chapter 5. We are really moving ahead now, aren't we? Okay, so in Chapter 5, we now, for the first time, are going to go backwards from derivatives. We're now going to do antiderivatives. But first, let's recap on the 3 most important subtopics or fields within calculus. And for that, let's go to a new segment called History Break.
Calculus is made up of 3 major subcategories: derivatives, integration, and limits. Derivatives were discovered in 1665 by number 3 ranked Sir Isaac Newton. Integration was discovered 2 years later by his professor, number 102 ranked Isaac Barrow. The 3rd category of limits will be discussed in the 2nd semester, modernized not until 1821 by a top 10 mathematician, number 7 ranked Augustine Cauchy. Sadly, Isaac Barrow died at the age of 46 and did not get to see the full development of what was to come in calculus. And those are the 3 major subcategories of the subject you're studying.
So as you can see from the history break, this is a momentous occasion today as we move on to the 2nd of 3 subcategories in calculus. You have done all the derivatives that you're going to need to do. We will come back to those later and apply them to real life problems, but we have done derivatives backwards and forwards. Now we move on to the antiderivative, the 2nd major theme of calculus, and we are going to basically go in reverse. And if I give you a derivative, you tell me the original function it came from. Lots of important real-life applications, of course. So we start with this. Let's practice doing one last derivative before we step into how to do an antiderivative, which will be more commonly referred to as integration, by the way. So how did we take the derivative of y equals 5 times the quantity 3x minus 2 to the 7th? Well, we wrote down y prime. The 7 came down to the front. We did 5 times 7. We won't even simplify that. It's 35, but the base stayed the same. The power dropped by 1. And then we multiplied by the mandatory chain rule. The derivative of the original base 3x minus 2 is times 3. And normally we would simplify that. We don't even have to simplify today. Just look at what you just did. All right? So let's take a look at 3 things, the 3 steps it takes to do a simple derivative. So step number 1, what did we do? We multiplied the coefficient by the exponent. So let's just write down exactly what we've been doing for so many weeks and a couple of months now, right? Multiply coefficient, we'll abbreviate it, by exponent. All right, that's step number 1. Now, step number 2, what else did we do? We immediately subtracted 1 from the old exponent, didn't we? Subtract 1 from old exponent. All right, 7 was the old exponent, 6 would be the new exponent. All right, and what was the 3rd and final step? Multiply by the chain rule. Mandatory, right? Okay, those are your 3 steps of a basic derivative, and you all know those by heart. So now we have a new proposition. Y equals 6, 2x plus 5 quantity squared, and you have to tell me, where did that come from? If that's the derivative, how do we get back to the original function? Okay, antiderivative, right? So what would be the steps? All right, I'm going to do the opposite because, of course, this is the antiderivative. It's the opposite of a derivative. So the first thing I'm going to do, instead of subtracting 1 from the exponent being the middle step, it's going to become my first step, but it's no longer subtract. This is opposite day, right? First thing you're going to do is add 1 to the exponent. So you would bump the squared up to a cubed. We're going the other way now. So exponent is now first priority instead of second priority. Now the first step in derivatives becomes the second step in the antiderivative. But it's not multiply anymore, is it? Divide the coefficient, which is currently 6, by the new exponent. Okay, divide 6 by the new exponent, not 2, but the upgraded 3. So it's backwards, right? And then finally, we're not going to multiply by the chain rule, which is the last step of a derivative. We're going to divide by the chain rule. So divide by chain rule. And then this is basically just totally opposite of a derivative, and it works. So now we're going to test it out. Let's say that the derivative f prime of x is this 6, 2x plus 5 quantity squared. How would you go back and find f of x for me? All right, let's practice. 6, 2x plus 5 quantity, no longer squared. We're going to add 1 to the power and escalate it to a cube. So derivative knocks the powers down lower. Integration builds up the powers, right? Antiderivative builds up the powers. So add 1 to the power, divide by the new power, which is 3. You could just divide the 6 by 3, like I said over here, the coefficient, or probably more practical to put the whole thing over 3, I think. Put the 3 under. And then finally, divide by the new power, but also divide by the chain rule of 2x plus 5. So you see there's always a chain rule, even in integration, antiderivatives, right? The chain rule of the original base, derivative of the original base, is 2. So you must also divide by that 2. And since the 3 and 2 are both dividing, they're both going to get together, right? They're in the same place. They both went downstairs. So 3 times 2 is 6. 6 over 6 is 1. And you get 2x plus 5 quantity cubed for your final answer. Now, do all you bright students out there in calculus know how to check your answer? How do you make sure that that's correct? Couldn't you just, I'm sure somebody's thinking it, take the derivative of that, and it should go back to this, the original problem, right? And it works. Okay, you can always check your answers. Okay, so that's the front page. Now we kind of got our feet wet with these new things called antiderivatives. Now we can really jump in the pool. So let's go over here to the next example. So in letter A, let's see what it's going to look like in this chapter. We've got this little curvy symbol, which is actually called an integral. And the integral means you're supposed to be integrating or taking the antiderivative. So this is a symbol. If it looks like a gigantic capital S that's been stretched, it is a capital S, actually, because originally it came from the Latin word summa. And summa means summation, to sum. So integrals are actually summing up a bunch of infinite parts, which we won't get into until much, much later, but you'll see that someday. So that's called the integral symbol, all right? Antiderivative or sum. And you know what? The person who came up with the integral symbol was none other than number 53 ranked, one of the Bernoulli brothers. They were major in mathematics, weren't they? This is Jacob Bernoulli, the highest ranked of the dozen or so Bernoulli mathematicians. There were so many that came out of Switzerland from the same family. Here's the deal. We have to integrate or do the antiderivative. You know what? I probably should have put that in a history break, I just realized, right? Number 53, Jacob Bernoulli. That should have been in my history. Let's put it in there right now.
Number 53 ranked Jacob Bernoulli from the famous Bernoulli family was the first one to propose the integral symbol. He was the same mathematician you'll remember from Integrated 3 who discovered the number e in nature, approximately 2.7, an irrational number just like pi.
All right, nice work. So basically, just like a derivative, you have to get this integration ready, just like getting something derivative ready. You don't want a radical. You don't want an x on the bottom. You got to fix that first. So this is the integral of x cubed plus, of course you would make that x to the 1/2, just like we did with derivatives. Minus 2 is the coefficient. Of course you would bring the x up and make it x to the -2 plus 5. That whole quantity. This quantity is called the integrand, by the way. If I ever refer to the integrand, it's the thing being integrated. It's the body of the problem. Now the dx, we haven't talked about that yet. When you write an integral, you must also write a dx. It's just kind of notation for now. Later in the second semester, I'm going to explain where the dx comes from. It will blow your minds how all this stuff ties together that you've learned. But we have to learn a lot of math in the meantime before I explain the dx. The best explanation for today is that it kind of represents basically the chain rule. It does kind of represent like the chain of any kind of base, essentially. Just think of it like that for now. Okay, now we can integrate. So the integration or antiderivative of x cubed, what's our new rule? Add 1 to the power, x to the 4th, divide by the new power, 4, also divide by the chain rule of the base x, which is just 1. So there is a 1 downstairs, you don't have to put it, but it's there because you always divide by the chain, right? Because the derivative, you always multiply by the chain. All right, add 1 to the power, x to the 1/2 plus 1 is 1/2 plus 2 over 2, which is 3 over 2. Divided by the new power, 3 over 2. Also divided by the chain rule of x, but it's just 1, who cares, right? Minus 2x, add 1 to the power, -1st, divided by the new power, -1, but also divided by the chain rule of x. 2x is not the base, right? It's not in parentheses. Just x is the base. Divide by 1 again, right? So the chain rule is not making a major impact yet. It will. The integration of 5. Whose derivative becomes 5? Isn't the derivative of 5x 5? So the integration of 5 goes back to 5x. You're just asking, whose derivative are you? 5? Oh, 5, you're the derivative of 5x, yeah. All right, go backwards. Now there is one last thing I want to mention here that we're going to put at the very end. But first, we're going to simplify, of course. We're going to make this look a lot nicer. And then once we simplify this, isn't the derivative of this thing going to be the original problem, or the original integrand, right? So the integration of that is that. The derivative of all this is integrand. But one thing, what if there was like a plus 57 at the end, or a plus 68, or a plus 2, or maybe a minus 16.87, right? What if there was a constant at the end of your original function? Wouldn't the derivative of a constant become 0 and you wouldn't see it up here, would you, right? Everybody see the derivative of 5x is 5, but the derivative of a constant would be invisible. So when you go backwards, you don't know what constant could have been sitting there. And it actually could have been nothing. It could be plus 0, believe it or not. But there is some constant, if you include 0, there is some constant that is there at the very end that disappears in the derivative process. So to handle all that, we don't put this on a test. That would be chaos, right? To handle all that, what you do is you put plus c. C is called the constant of integration, all right? Constant, things in the way of integration. The constant that could have been there, and I'm completely running out of room. Integratio, and that is integration. Constant of integration is the constant that could have been there and disappeared in the derivative process, okay? And again, if you include 0, then yeah, there definitely has to be something there. That even includes like the subtraction one I gave you. The minus 16.87, well, that would be plus negative 16.87. So this covers all the addition, subtraction, or even 0 that could have been there, okay? So make sure you put that at the end. And now we're going to fix this and clean it up. Okay, first of all, this is x to the 4th over 4, drop the 1. What I prefer, personally, you don't have to do this, but I really prefer to write that as, isn't that really 1/4,
right there. It's not 4, it's 1/4, right? I prefer to move the fraction out. I think it's better practice for what we're going to do in the future. 1/4 x to the 4th. You will never get counted off if you put x to the 4th over 4. That's completely fine. I think this looks better. Now, remember, keep, change, flip. Dividing by 3 over 2 would be multiplying by the reciprocal 2 over 3. Keep, change, flip. All right? So write that as 2/3. Now, x to the 3/2, that's fine. I'll give you full credit. I'd rather you go back to radical form, just like the derivatives. So I'd rather you go back to x to the 3rd power 2nd root, and that's going to be better. Okay? But again, I'm not going to count off points. And then finally, a minus and a minus makes a plus. Let's take care of that. 2 over 1 is a coefficient of 2, and we don't leave negative powers. X to the negative first is actually x to the positive first on the bottom. Okay? Plus 5x, and then every time you do an integration problem, an antiderivative, put plus c. Okay? Technically, the only difference between integration and antiderivative is the antiderivative is without the plus c. It's just the generic rule of going backwards. And then integration is with the plus c. That's not a big deal. So just always put a plus c, because you will need it for sure. Now, we just did an extensive problem where we had to prepare the integrand to be integration ready. And did you notice it was just like preparing a derivative to be derivative ready, right? So when you see a problem like this, let's say this were a derivative. Let's say you were taking the derivative of 1 over x. Wouldn't you prepare it for the derivative by immediately bringing the x to the top and making x to the negative first, right? And remember, the integral always goes hand in hand with the dx, okay? Now, when you integrate x to the negative first, this one is an exception to the rule, all right? For derivatives, you always want to bring your x up. For integration, you always want to bring your x up, except in this case right here. I'm going to show you a little anomaly that happens, all right? The exception to the rule. When you have x to the negative first, if you add 1 to the power, isn't that our first rule, right? Add 1 to the power, you'll get x to the 0 divided by the new power, 0, also divided by the chain rule of x, which is 1. And then you put a plus c at the end of every integration problem. Everybody see what happened there? But wait a minute. You can't divide by 0. Oh no. That does not exist. Okay, so let me get this straight. So the integration of 1 over x does not exist. So does that mean the derivative of does not exist is 1 over x? So the derivative of absolutely nothing in the world is 1 over x? That can't be right. No. No, that's a big disaster. That did not work out properly at all. Okay, this one is an exception. All right? Let's try it again. Okay, this is what you should be thinking. What you should be thinking is, yes, I have rules I need to follow, but whose derivative are you? It's our new favorite game called Whose Derivative Are You? All right? There is a derivative we took back in the derivative chapter where the derivative of that thing turns into 1 over x. All right, whose derivative is 1 over x? It's not D and E, that's for sure. Okay? Does anybody remember that the derivative of natural log becomes 1 over x? Therefore, the integration of 1 over x goes back to natural log. It's a special case. And you will not get there adding 1 to the power and dividing by the new power. Okay, this is the anomaly. If it was 1 over x squared, you could do add 1 to the power, divide by the new power. Okay, if it's 1 over x cubed, you can do the method we did on this board over here. If it's x squared, x cubed, x to the 4th, x, all those work. It's just 1 over x to the 1st where the rule does not work. So just remember that it's natural log of x. Now, one little twist, when you go backwards, you put absolute value bars on the x. I'll explain that later because it'll be vital later on. So when you go backwards, put the bars on the x, okay? Plus c. And now you have the only function whose derivative will return to the integrand 1 over x. And it works, all right? And since c actually has infinite possibilities and we don't know what it is, instead of calling this one function, they often will call this a family of functions.
Okay, technically it's infinite different possibilities, so this is the only family of functions whose derivative is 1 over x. Now, challenge us. All right, let's try this one. This one really drives home the difference between is it natural log like we just did, or is it not natural log? Okay, does everyone see that x to the first is on the bottom, just like the last problem? X to the first is on the bottom, all right? Now this one over here, see this 2x? That is also x to the first though. One of these is natural log, one of them is not. You see how this is x to the first and the plus 1, that's not going to change it. It's x to the first. This is the one that's the natural log right here. It's x to the first unobstructed by anything else, okay? And the plus 1 does not hurt it. This is x to the first, but quantity to the 7th. That's not a natural log, okay? Not natural log, okay? Because the 7th power. So you have to have x to the first, but you also have to have quantity to the first and nothing else. Both have to be first. If it's first power, quantity, anything else like 7th, that is not a natural log, okay? That's the difference I want every calculus student to see, because you've got to integrate a lot of these and you're going to integrate a lot of these. So let's try to get this integration ready. You do not need to change this one, okay? That one is what it is. It's going to be a natural log. Do not bring that up and make it 7x plus 1 to the negative first. Don't do that. Is that true? Yeah, mathematically that is the same thing. But that's going to force you to add 1 to the power and divide by the new 0, and it's going to ruin everything. So it doesn't work, okay? So then this one, 24 is the coefficient, minus 24 technically. Bring this one up. 2x minus 3 to the negative 7th, right? If it's to the negative first when you bring it up, put it back downstairs because you're going to do a natural log. If it's to anything that's not negative first, that's what you're supposed to be doing. You're supposed to be doing the add 1 to the power rule, okay? All right, there we go. Now, 7 is the coefficient. Okay, we haven't done this yet today. The coefficient carries. It always stays. It's 7 times what it would have been. This is the natural log of the absolute value of x plus 1. All right? But we always divide by the chain rule. We didn't mention that over there. It wasn't important yet. You must divide by the chain rule. And the chain rule of the base x plus 1 is 1. Okay, so if you forgot it, you would have lucked out. Not over here. Minus 24. X to the first, but not negative 1, so it's not natural log. You keep the base the same. You add 1 to the power. Negative 7 becomes negative 6. Divided by the new power, negative 6. And divided by the chain rule, which you must divide by. I think it's the first time we've had one. We've only had like 1 so far for the chain rule. Chain rule of the base 2x minus 3, the derivative is 2. And you must divide by the new power and the chain rule. And you must put a plus c. Does everybody notice once you integrate, once you physically do the integration, does everybody notice that you lose the integral and you'll lose the dx? Okay? Those are just for notation to tell you to integrate. Once you integrate, drop those off. And really you put a plus c instead. And the best explanation, without getting into a lot of theoretical calculus that we'll get into in the second semester, the best explanation is the dx represents the chain rule. What does the chain rule do when you take a derivative? It jumps out and attaches at the end, right? When you integrate, the chain rule is actually going back inside and disappearing, if you think of it that way. Okay? It's unchaining itself, sort of. All right. So there's that. Now this is a mess. I mean, you get most of the credit for doing this, but you really need to straighten this out. So final answer, drop the 1. 7 natural log absolute value of x plus 1. Okay. Oh, minus over a minus is a plus. 24 over 12 is going to be 2. And you don't leave negative powers. So you take this and you throw it back down to the bottom. 2 positive 2 over 2x minus 3. Quantity to the 6th plus c. And that, my friends,
is how you do integration. And that's how you spot natural log and not natural log. Students sometimes get that confused and it can cause disasters, all right? So there's your setup. Okay, let's try example D. Now this one's going to be quick and easy. You can do it in essentially one step. Again, we're getting into some trig functions now, right? You have to be able to integrate trig functions. So again, you're just saying to yourself, whose derivative are you? There's no add 1 to the power, divide by the new power here, okay? That's only for things that look kind of like polynomials, right? X to a power, basically, number x power. Okay? Even square roots and x's on the bottom, which are not polynomials, but they're algebraic, right? So now over here, for trig functions, don't add 1 to the power, that's not part of the rule. Simply, okay, you see the 3? Carry the 3, coefficients carry, and then ask yourself, cosine, whose derivative are you? What derivative did we do in an earlier chapter where the derivative landed on cosine? The derivative of sine is cosine. Positive sign, right? Okay, so now students get this backwards. So you really got to train your brain to do this. The derivative of cosine was negative sine. You all remember that. The integration of cosine is positive sine because it's opposite world, right? So make sure you do that. By the way, divided by the chain rule of base x, which is just 1. All right, secant squared. Whose derivative are you? What derivative did we do earlier where your derivative must be secant squared? Remember the derivative of tangent is secant squared? So the integration of secant squared goes back to tangent of the base 2x over the chain rule of the base. Derivative of 2x is 2 plus c, all right? And again, you could do that in one step in your head. We'll go ahead and take a second step just to clean this up, but you could have skipped this step and just gone straight to the answer. Drop the 1, you all know to do that. 3 sine of x. I prefer this as a 1/2 in front instead of over 2. I think it looks better. I think it'll help you for future endeavors. You don't have to do it yet, but I would suggest it. 1/2 tangent 2x plus c, and that is the only family of functions whose derivative goes right back to the original problem, the integrand, okay? So now I have a 5. I'm going to carry the coefficient 5. Sine, wait a minute, whose derivative was sine? Whose derivative was sine? Not cosine, negative cosine, all right? Be careful. The integration of sine is negative cosine of x. See, I put the negative in front of the 5. Don't you dare put 5 and then minus cosine. It'll look like subtraction, right? Put that negative in front of the 5. So remember, here's another way to remember this. This is opposite world. The derivative of sine is cosine. So the integration of sine is negative cosine. Think opposite, okay? Negative cosine. Now, minus 6. Okay, ooh, tangent. Yes, there is an integration of tangent, all right? A lot of the common functions we study, they have integrals, they have integration, they have antiderivatives. We never did a single derivative that landed on tangent, okay? We have not done that at all. So we need to add this to our integration rules. There are only 9 major things we can integrate very commonly in calculus. That's it, okay? And this one might be one of the final ones. I think there are only 2 more I have to teach you after this. So how do you integrate tangent? Whose derivative is tangent, since we never covered that before? It is natural log of absolute value of secant of 3x. Natural log, absolute value, secant of whatever the base is. Now don't forget to divide by the chain rule 3 from the 3x. And over here I didn't mention it because the derivative of x, or chain rule of x, is 1. So this is over 1, but you don't need to put it, right? Okay, and then of course, put the obligatory plus c at the very end, and now you've got an integration. Now, how do calculus students mess this one up on the test? Oh, you find ways, let me tell you, you find ways to make silly mistakes, because you're all brand new at this, okay? You don't have the advantage of doing this for decades, and I know that. So students on the test often put natural log of secant squared. Where the heck did that squared come from? That's not in the formula. You know what your brain does? Your brain is so used to the derivative of tangent is secant squared back in the old days that when you see tangent, your brain wants to spit out a secant squared, but it's not, okay? It's just natural log secant. Okay, I'm going to drop the 1. I'm going to make it -5 cosine of x. You're just going to memorize this rule. That's all it is. It's just a memory thing. -6 over 3 is -2. Natural log absolute value of just plain secant, without the squared, of 3x. And hopefully you all learned back in pre-calculus that secant is 1 over cosine. It's just the reciprocal of cosine. We just have a name for it, okay? Easy stuff. Just know your rules, all right? Okay, we've almost covered all the integration rules. Now, in letter F, it's not really a problem. It's just a question I want to address today. Here's the discussion to be had. You're all integration rookies. You're all brand new to integration, which is totally cool. So you don't really know right now what you can do and what you can't do. Mr. Wade, what can I integrate? What can't I integrate? Well, you can't integrate these things yet. Okay, and you're too fresh with integration to know why until I show you. So chapter 5 is about developing those skills. Why can I not integrate sine of 3x squared dx? It looks so similar to the things we've done today. There's a minor difference, okay? Does everybody see the chain rule of 3x squared? What's the chain rule of 3x squared? The derivative of 3x squared. Wouldn't that be 6x? Okay, something just happened that has not happened yet today, and I want you to see if you know what it is. The chain rule contains a variable. Haven't all the chain rules today been constants? All right, so beware. You cannot integrate sine to be negative cosine. Didn't we say the integration of sine is negative cosine today? You cannot integrate it to be negative cosine and then just divide by 6x and put a plus c on it. That is absolutely not true at all, okay? This is way more complex than that. Does not work. So, what's the problem? If the chain rule contains a variable, you can never just randomly divide by it. That would be introducing another variable into a problem. You can't introduce another variable. Constants are fine, like numbers can come and go, but not variables. That completely changes things, all right? Impossible. Look at the chain rule of this base right here. 4 times 5 is 20. X to the third plus 2 becomes plus 0. The chain rule contains a variable. You cannot add 1 to the power, divide by the new power, and then divide by 20x cubed. You can't get away with that, okay? So I want you to remember this. This is very, very important here. In the homework, all the cases, you're dividing by a constant when you divide by the chain, so make sure you do it. In some of the future sections of chapter 5, we're going to have cases where the chain rule contains a variable and you can't do this rule, but you can convert it to an easier case where you can use the rules, okay? So that's going to be a later thing that we have to grapple with. If the chain rule is a variable, convert it to where it's not any longer. We don't know how to do that yet, okay? So remember this difference between I can and I can't integrate. Try the homework, watch 5-2 when you get a chance, and we will discuss it.